Okay, from now on, let's talk about top-down enumeration algorithm, which start from the start non-terminal and gradually expand non-terminals using production rules in the grammar. Okay. For example, suppose we use a top-down style enumeration algorithm to find the solution of this problem, okay, which is find the function f, okay, that takes two arguments and satisfy this condition. Okay. Intuitively, what is the solution? Okay. Intuitively, f x y equals to x plus y. That is the solution that we want. Okay. So the synthesizer tries to find this solution, okay, using this grammar. Okay. And then the search algorithm enumerates programs as follows. So initially it starts from the starting symbol S here, okay, and then it gradually expands the non-terminals using the production rules from the grammar. So at first, once it expands the starting symbol using, okay, this rule, okay, then we have these programs. Okay. As you can see, some of them are all grounded, which means no non-terminals. Okay, all of them are terminal, but some of them have non-terminals like this. Okay. And the algorithm check whether the grounded programs, such as this one, okay, satisfy the condition or not. As you can see, any of the grounded programs so far, X or Y, they don't satisfy the specification here. Then next, it tried to expand non-terminals like this, okay, from the ungrounded candidates, okay, one by one, and repeat this process until finding the solution. Okay. As you can see, after some iteration, it will find a right program, x plus y. Okay. That is the high-level description of top-down enumeration. As we have seen before, the search space is very huge, so we need an efficient search space pruning techniques that discard redundant or unpromising subprograms as early as possible. See, this is actually a static analysis problem in that it has to estimate programs' behavior beforehand. But in this lecture, we simply consider simple equivalent checking heuristics here. For example, according to the semantics of plus, okay, we do not have to consider both type of candidate program like this. Okay, all programs generated by the first, okay, sentential forms will be also in the set of programs generated by the second form, right? So we can discard one of them. Okay. Same as here, we can discard one of them. As you can see, all the programs, okay, when we search through this space, it will be the same as this part on the right hand side. So we will discard this thing. Okay. So here is the top-down enumeration algorithm. So given a grammar G and a specification pi, okay, in our case it is the input-output examples. It starts from the starting symbol here and enumerate all possible candidates. Okay. For each candidate P, if it satisfies the specification, then we are happy, so it returns the program P. Otherwise, it unrolls non-terminal symbols in the program, okay, by once using the production rule. Okay, that part is in the unroll function here. Okay, this in the unroll function for all non-terminal A in this program P. Okay, for all production rule A to B in grammar G, it replaces A to B. Okay, this means replace. Okay. Then we collect all of them. Okay. Again, this unroll, this function actually expand the non-terminals by ones using the production rule. Okay. Then coming back to the main loop. Okay. The only thing is this part. The remaining things. This subsumed. Okay. That actually checks whether this new candidate P prime is already subsumed by another candidate, as we discussed in the previous slide. Okay. If not, then we add this program as a new candidate, like this. And we will keep repeating this process until we find this solution. Okay. As you can see, this process may not terminate. So for that, we need some stop criteria, such as timeout. Okay. Then next, let's talk about bottom-up enumeration, which starts from terminals rather than non-terminals and gradually combines subprograms into larger ones using production rules in the grammar. Okay. For example, suppose we use a bottom-up style enumeration algorithm to find the solution of this problem. Find the function f that takes two arguments, again x and y, that satisfy this condition. Okay. Intuitively, what is the solution? This specification describes that if x is larger than y, then x, otherwise y. Okay, so fxy is equal to if x is smaller than y, then y, otherwise x. Does that make sense? Okay. So the synthesizer tries to find this solution, okay, throughout the same grammar. The algorithm here, the bottom-up style algorithm, enumerates programs as follows. Okay. It starts from all terminals of the grammar, like x and y. Okay. But as you can see initially, both of them are not the right solutions. Okay. In this case, it combines the smaller programs to make larger programs using the production rules in the grammar. Okay. In this case, for example, using x and y, we can make x plus y, x minus y, okay, like this. And also this comparison expressions. Okay. Once we have this, okay, these smaller expressions, we can combine these smaller expressions to make larger expressions like this. So using all of the smaller expressions. Okay. And the synthesizer repeat this process until finding the solution. Okay. As you can see, after some iterations, it will find a right solution. Like this. For the bottom-up approach, again we need a proper search space pruning method. The principle is the same. We have to discard redundant or unpromising subprograms as early as possible. So, but a bit different thing from the previous top-down case is that here all candidate programs are all grounded. That means no non-terminals, but might not be whole programs. That means we don't know how these subprograms will be combined later on. Okay. Then how can we prune the search space? But notice that in programming by example setting, the inductive synthesis setting, our goal is to satisfy only a given input-output examples, okay? Not any arbitrary cases. So we can use this property. So we only care of equivalence on the given input. Okay. This kind of equivalence is called observational equivalence modulo this input. Okay. For example, These two programs are observationally equivalent modulo these two inputs. Okay, their input-output behaviors are the same modulo these two inputs. That means this program can be always used instead of the other program under the input-output specification. Okay, that means again, whenever this program is used in the solution, you can instead use this program because their observational behavior modulo this example are the same. So these two are interchangeable. In this case, we can consider only one of them. Okay, that is a simple search space pruning technique based on observational equivalence. Okay, this is the bottom-up enumeration algorithm. Starting from all terminals of the grammar tree, it repeats the following things. If a candidate program P satisfies the specification, then we are happy. We return the solution. Otherwise, it grows the candidate set. Okay. Let's take a look at the function grow here. For all production rules in grammar G, if there exists a non-terminal G that can derive this terminal P, okay, then we replace all C in B to this terminal P. Okay, what does that mean? Suppose we have this simple grammar x, y, x, s plus s. Okay, and here suppose we have terminal x and y. Okay, then what does that mean? This x and y, this x and y can be derived from this x derived from this symbol s, right? This one. Okay. Then what does that mean? Then we can pick up this rule s plus s, okay, and replace all s with x or y. What does that mean? Then we can derive, which means we can combine these two terminal symbol with this plus, so we can generate x plus y, okay, y plus x, okay, and x plus x, y plus y. Okay, that is what this line means. Okay, and then next, coming back to the main loop. Okay, as we discussed before, we will discard candidate programs if their observational behavior is the same as other candidates. Okay, this check is done by this equivalent function. Given this specification, okay, if there exists a program whose observational behavior is the same as this one, then we will discard. Otherwise, we will collect this one as a building block. Okay, that is the whole structure of bottom-up enumeration.